Hey everyone, good morning. Let's welcome Dr. Geoffrey Thomas. He'll be speaking on what's new in Linux kernel from Python. Let's give it up for Mr. Thomas.
All right, thank you everyone. Good morning. And we are going to be talking about how to use new features in recent versions of the Linux kernel from Python. So just to set expectations, this is not a talk about writing the Linux kernel itself in Python. It's about using new features that the kernel provides to applications. The kernel's API is defined in terms of C, and we'll talk a bit about why that is, but it means that you need to know a little bit about C to make use of these features directly, but only a tiny bit, and we're going to go through every bit of C that you need to know, so as long as you can read Python, you'll be okay. Also, everything that is up on screen, plus some more details and notes, is up on github.com/jeft/pycon2025. If I move quickly, don't worry, you can clone that and follow along. So let's dive in. What are these new kernel features, and why would you even want to use them? Let's start here. When you run open file.txt.w, as you probably know, this opens a file for writing. If it doesn't exist, it will create it. If it does exist, it will open it and overwrite it. How do you tell which one happened? And it turns out that the people who write systemd, which is a base piece of software on many Linux machines, which is not even a piece of Python software, had this problem. There isn't actually a real way to tell. And they said, hold up, surely the Linux kernel knows this. It's the kernel that creates files for you. Surely it has information to know what it did. Why can't it tell us? And so they added this feature. And on the left here is an article from LWN, which is a Linux news site, on changes in Linux kernel 6.12, which I've trimmed a bit of, but you can see there is a new fcontrol operation, fcreated query, that allows an application to determine whether a file opened with ocreate was actually created rather than already existing. So a bunch of terms there, and I have the full commit on the right, or the commit message, actually half of it because it's a very long commit message. Don't worry about reading that. We'll talk about what all of this means. So starting up with fcontrol. Fcontrol stands for file control. It is a system call. A system call is a way for a normal non-kernel program to make a request for the kernel to do something. So it is kind of like a function call, but it is also kind of like calling an API on a server, like a network API, because you are asking the kernel, which is more powerful than your application, to do something on your behalf and get you the answer. And so just like with APIs for network services, sometimes there are wrappers for kernel APIs. If you want to talk to, let's say, I don't know, GitHub, you could import requests, make a bunch of HTTP calls directly. There are also great wrappers around the GitHub API, like, I don't know, GitHub 3, whatever's popular today. So in the same way, the Python fcontrol module is a wrapper around the kernel fcontrol API. And so we need to figure out how do we use this API, and unfortunately, there isn't really a lot. Actually, sorry. Let me go back a little bit. Just like with the network API, you're going to have to think about what's really happening underneath with the underlying calls that are happening to make full use of the wrapper in Python. And one thing you'll notice if you read this Python manual page, this is part of this Python standard library, but that operation that was just added, fcreated query, is not on here. And there's a couple of reasons for that. One big one is that it's new, but the other one is they didn't really document this anywhere than adding the code to the kernel. And that unfortunately happens a lot, and I sympathize with that. Like, you write some code and you gotta write them docs too? Like, I just got the feature working. But it is very important to be able to figure out sort of just enough about what is this feature that has no docs. And I gotta say, I think that being able to search source code and like figure out just enough of a large project to track down the info you need and not get lost is a valuable skill. So let's do that. Before we do that, I want to talk about a few good ways to do it. For anything that's on GitHub, if you're logged in, there is a good code search. There is a company called SourceGraph. They make a commercial product, but they also have a public code search as kind of a tech demo that searches GitHub and GitLab and a couple of other things. Debian code search will search anything that's in the Debian Linux distro, including stuff that isn't in Git at all, just like very old and very rarely changing stuff. And of course, if you have a git clone, there is the git grep command. So I'm going to take a git clone of the Linux repo, because I happen to have one, there's many ways to do this, and search for this fcreated query. And here's all the places we see it. The first search result is what looks, first line here, is what looks like the implementation in fs/fcontrol.c. And then the definition of it on the next line in an include file for the UAPI, the user space API, that's what we want. And so fcreated query is defined as flinux specific base plus 4. What is flinux specific base? We can do another search for that. It is 1024, so we know that our fcreated query is 1028. Hold on to that number for a second. And then below this, I put a larger snippet of this first search result we got with the implementation. By the way, if you do this search yourself, you will see a couple more hits in the tools directory. Tools are applications that source code is kept with the Linux kernel, but is not actually part of the kernel. So we can ignore those. On the other hand, one of the tools is tests. So maybe the Linux kernel test cases will tell you how to do something. In our case, we can just read the implementation. If you know what you're looking for, it's easy enough to follow. If you remember the Python docs from 2 slides ago, the definition of this function matches pretty closely. It takes a file descriptor, it takes a command, it takes an argument, it takes a file pointer to the file descriptor because that's what the kernel uses, so it's convenient for the kernel to pass it. You can ignore those next few lines and go down to the switch statement, which is basically C's version of Python's match statement. Very conveniently, the first thing it tests is fcreated query, and it calls a helper function with the same name. And the important thing about this function is that the argument, this arg parameter is unused, which makes sense. We don't need any other information besides the open file to ask, tell me whether this file was created or not. It's a very simple question. It has a yes or no answer. So now we know enough to go try it out in Python. And so I'm going to open a Python shell. I'm going to define fcreated query because no one else has defined it anywhere in Python, pulling the fcontrol model. And so I'm opening this file, foo.txt, and I ask, what is fcreated query for it? And it says 1. And I close it, and I open it again, and I call it again, it says 0. So that's essentially the answer to your question. And so we can wrap this up in a very small Python library like this. Just define a function, put a little wrapper around it that turns into a Boolean. Honestly, this does something, maybe I should upload this to PyPI. This does something that nothing on PyPI currently does, even though it's only 4 lines long. And to be fair, I did choose to start this talk with an example that is pretty easy to use in Python, but I don't think this is actually an unrealistic example. Python, as you may know, is a language that has found a lot of success in gluing together C code and gluing together libraries that already exist, etc. So many times you might find that someone has already written a Python wrapper that gets you most of the way there, but there's a new feature that needs a new constant or new flag or something. And all you need to do is know how to find the value of that constant and know enough about the wrapper to figure out how to pass that on. So that's what we're doing here. But let's look at something that is going to be a little more involved to access from Python. One of the things that Unix, meaning Linux, Mac OS, many other operating systems, has this concept called everything is a file. Everything that you can treat as something you can read, write, open, close, etc. They want to try to structure it as files because there's already like an API for it. And so there is a file system on Linux called procfs, or just proc. And I call it a file system because it has directories, it has files, it has contents of files, but it's not anything that's actually on a disk anywhere. It's just exposing information from the kernel. And in particular, if you go look, you will see that every process on your system has a directory named after the process ID. And if you go into one of these directories, there's some info about what is the process, what command is it running, how much memory is it using, etc. And this is actually how tools like PS, LSOF, top work. They'll go look at the proc directory, they'll get the list of subdirectories in there for each process, they'll read some files and do some analytics on it. And the nice thing about proc is it's almost all plain text files. So if you listen to nothing else for the talk except the last 30 seconds, you now know enough to go write your own versions of PS and top and LSOF in Python just by going and looking at these files and reading them with the normal tools for accessing files in Python. And I think that's really cool. But actually, let me show you an example of a certain file here. This is proc self. This is proc maps. Proc self, by the way, always refers to the current process. So I'm using that for convenience. Just keep in mind the results will change if you look at it in multiple processes. Proc whatever maps is a file that lists all the memory mappings of the process. Memory mappings means when you go access some memory, here's where it comes from. Maybe it's a normal memory allocation and it doesn't have a name. you'll notice that things that do have names are the program itself and all the libraries you're using. And libraries in Python include compiled extensions and the libraries they're using. So, NumPy, Torch, the NVIDIA CUDA libraries, OpenSSL, et cetera. When those are loaded in your process, this is how you figure out what is the actual thing, the exact file it loaded. And so, by the way, this feature is not new at all. Proc has been around in the Linux kernel for decades. But I want to demonstrate this first with text. This is something I've done, countless times. I did it last night to debug. Hold up, which version of this library did I just import? Like, where did I get it from? And you can open up the proc maps file. You can get the last thing after calling split on it, and print out everything you see and get a list of libraries in Python. And that's great. This is exactly how things like LSOF work. One thing that's annoying about text files like this with file names is that file names can have really any characters in them, like spaces. And so if you do the obvious thing of calling split, like I'm doing here, it's not going to work totally right. There are rules for how to parse this text correctly, but the kernel is obviously not storing it on its end as text. It's storing it in some data structure somewhere. You want it in a data structure so you can work with it. Like, why are you putting it into text why are you asking the kernel to turn it into text just so you have to pull it right back out of text? And this is a problem that some really high performance profilers, not written in Python, ran into. They also had other things they wanted, like I want to see some of the results. I don't want to see all of them in sort. I want the kernel to answer specific questions, et cetera. And so they added this API in kernel 6.11, which was released last September, to get the proc maps info in a binary format. And so the motivation was not Python users, but that doesn't mean we can't use it from Python. And I'm going to go do that just as a sort of thing to explore. And so this is a much more complicated interface, the one that they added, compared to the one we just looked at. And it has a few moving parts. It starts with this particular structure for doing the query. There's documentation, if you go look at the actual source in the kernel, of what all these fields mean. I took that out just so you can see it all on one slide because we want to start thinking about the structure just to see how we would access this from Python. So ignore what these fields mean for the moment. This is C's equivalent of like a Python, mostly like a Python data class. It is an object that has a bunch of data types inside it. And so a little bit of a side note, why are we talking about the C programming language at all? Like, why is the Linux kernel written in C? And it doesn't have to be. In fact, fun story, you might know there's parts of the Linux kernel that are in Rust. That actually started right here at PyCon in PyCon Cleveland in 2018 at Sprints. So brief aside, if you've never been to Sprints, I do recommend it. It's something special. The PyCon organizers booked some space, like some of the open space rooms, for several days after the main conference, and a whole bunch of people with all sorts of backgrounds who maintain all sorts of projects have traveled here. And so you can go work with them and the projects get important things done because it has people in the right place. And several years ago, Alex Gaynor from the cryptography project and I were both at Sprints, and we said to each other, hey, I wonder how hard it is to get something in Rust in the Linux kernel. And we did that. It has nothing to do with Python, but that's okay. Seemed like it was good for the world. So that's how Rust got into the Linux kernel, but C. C is sort of the lingua franca of computing. It's kind of like any lingua franca, it's kind of historical. There was nothing unavoidable about it. It could have been another language, but it is convenient in a few ways for low-level programming and interoperability between languages. And one big reason is that the data types for C are very simple. Compared to something like Python, there's no generators, there's no async functions, there's no classes, there's no meta classes and inheritance. There aren't even dictionaries. C has very few data types. It's got numbers, integers, and floats. It has pointers, which means here is the memory address of some other piece of data. Here is a pointer to that part of memory. That's ultimately a number. It has arrays, which are fixed length. If you want to resize an array, you have to do that yourself. This is not like Python's lists. And it has structures like this, and that is basically it. What about strings? It doesn't really have Python-style Unicode strings. It's got bytes. Bytes are integers below 256, so all it does is arrays of integers. And so it's a very sort of simple data model. And every data structure in C more or less defines what the actual encoding in bits and bytes is relatively precisely, which is also why, as you might see here, types are not optional in C. You have to put a type on everything. And to be extremely precise and consistent, the kernel uses these type aliases for 64-bit and 32-bit integers, which you see here. So this structure in memory is exactly 64 bits for size, 64 bits for query flagged, etc. Enough C. Let's turn this into Python code so we can get a better, so we can read it better. And Python, of course, doesn't really care about the size of integers, so all of these are going to be ints. And we do need some way to turn this back and forth between the Python version and the C version. And you can see the value of C being lower level here. This data class doesn't tell you anything about how it's stored in memory, what the bits and bytes are. If you're just doing some calculations, that's actually very helpful to not have to think about it. That's one of the great things about Python. If you need to store this data structure in a way multiple languages can use, or even different versions of the same language, you have to be extremely precise about how you're storing things. So Python has another module in the standard library called struct. Struct converts back and forth between Python types and binary encodings and bytes. And so in this first line here, I'm asking it to pack 3 integers, values 1, 2, and 3. These are being packed as 32-bit integers, so each one is 4 bytes, 32 bits. And I get this bytes object back. I've formatted in the next line. It might be a little easier to read. So there's 4 times 3, 12 bytes long. And I can also unpack bytes back to a Python tuple. Here is a format string for a single integer, and I pass in these bytes, and I get a 1 integer tuple back. And one thing you have to think about when you're thinking about actually laying out bits and bytes is which order do the bytes go? Should I have written it as 5000 like I did here? Should I have written it as 0005? There's good arguments for both. 0005 is, of course, closer to how we do numbers in human writing. The 1's digit is right at the end. The bigger ones are before that. The other direction, the advantage of this, is it's easier to convert between sizes. If I want a 64-bit integer, I could just add some zeros. If I want a 16-bit integer, I can just drop some zeros. I don't have to move data around. And different CPU architectures meaning x86, ARM, et cetera, different architectures will make different decisions here. And if you're passing binary data between different kinds of computers, so if you're like working with JPEG files or MP3 files or something, you got to go to look at the JPEG or MP3 standard, and it will say, oh, we store all of our integers as big endian or little endian. This is what this is called. Right now, we're just talking to our own computer's kernel, which is going to use whatever is natural for the current CPU. And so this @ sign in this format string means use the native byte order. And so that should be enough to understand what struct is doing and what these format strings mean. So I'm going to go back to my data class I just defined for this structure. And I'm adding a little constant here. I'm actually going to make a compiled struct object. This is sort of the struct equivalent of re.compile to make this easier. And so right now, this is saying I want to pack 9 longs, meaning 64-bit, 4 integers, meaning 32-bit, 2 more longs at the very end. And so this corresponds to the C structure we saw. And also I want to note this size field. That is the size of the structure itself. And you might say, well, why is that important? The kernel in the future might add some more fields, and it wants to know how big you think the structure is. All the new fields will always be at the end. And so if you pass it the size of an older version of the structure, the kernel will just not look for those fields. Right now, there's only one version because this API is like less than a year old. But this is a pretty typical approach for backwards compatibility for kernel APIs and C APIs in general. Right now, I'm just setting the default value for my data class to the number of bytes that this struct says it's going to take up when packed. And so just floating here on the right of the slide is an example. Suppose I just called struct.pack of whatever these values are, struct.size, 00, et cetera. It'll get me a list of bytes back, 104, 00, et cetera. So that's what this struct.pack is doing. It's turning back and forth between the data class and bytes. I'm going to just jump back to the C code for a bit, just to figure out what were all these fields anyway. And one thing you might note is that many of these have a little comment saying out. And this goes down to how C is a very low-level language. You have to think about memory management. You can't just ask the kernel for something and it'll just say, here is some data. You have to make some space for that data to go into. And so for this API, the way they chose to do this is they designed a single structure where you fill in a little bit of it for the query, and the rest of it gets filled in the response. And so you'll see there are 6 parameters that are labeled in. There's the query flags, which indicate what sort of thing are we asking for. There's the address, which says where in memory do we want to see a result from. There's these two pairs of parameters called VMA name size, VMA name address, and build ID size and address. By the way, VMA stands for virtual memory area. Every line we saw in that procmaps output is a single VMA. So this name field here is the file name. And you might say, isn't that an output from the kernel? Like, why is it marked in or in/out? And again, manual memory management. What we're actually passing in is a buffer, some region of bytes that we've set aside for the kernel to put the answer into. And we want to pass in a pointer to that buffer, so the address, the location of that buffer in memory, that pointer is not changing. The kernel is just filling it in. So that is an input-only parameter. The size we pass in is the available space. The kernel will fill in at most that many bytes, probably less, and it's going to respond with the number of bytes it used. If it fills in exactly that many bytes, maybe it ran out of space and we should try again with a bigger buffer. I'm not going to do that now, but that's something your production code would have to do. And then looking at the rest of the out parameters, there's VMA start and end, which is the addresses we saw of what this VMA is. There's a flags field, but there's a bunch of other details, all of which is interesting. Right now, we're only interested in file names, so we don't need to look at them. For the query flags field, this very first input field, another part of the C API tells you what the flags could be. And then the first few let you filter by the permissions on the VMA. Is this read-only? Is this writable, et cetera? We're not going to bother filtering on those. And then these last two are only in the query flags. The other four can be in the response flags too, just to give you some info. And they're both interesting to us. So procmap query covering or next to VMA means if I give you an address and it doesn't point to a VMA, instead of telling me I can't find it, tell me about the very next VMA afterwards. And so we can use this to loop through all of the VMAs. We start at address 0, which is maybe hopefully unused. It's a null pointer. And we say, tell me about the next VMA after that. And it responds with the end address. And we take that address again and we say, tell me about the next VMA after that. And we can loop through and get all of the VMAs. And then this last flag, procmap query file back to VMA, means only tell me about mappings that come from files. Because that's what we're interested in. We're interested in libraries. There's other VMAs for normal memory storage, like your heap, your stack. We don't want to see those, so the kernel will let us skip those. And going back to my data class, I'm going to add some helper methods just to make this a little easier to use. Here is a pack function, which just calls struct.pack, and here's an unpack function. The struct module works with tuples. I've got a data class, so I'm going to call data classes as tuple to get in the format the struct module wants, and I'm going to splat that into the constructor to get it back into the data class. And then finally, we have our actual, let's use this API. And so this is an ioctl, which is short for IO control. And ioctl and fcontrol are both extension mechanisms for doing something special to a file descriptor beyond reading, writing, usual things you do. I can't really exactly describe the difference. It's a little bit vibes, but one of the important things is ioctl is more about the actual type of file, and fcontrol is more generic operations. And that brings us to the next challenge, which is we need this value of this procmap query constant. And that is not as easy as it was with the one we just saw. This is how it's defined in the kernel. Because ioctl operations are specific to the type of file, there's a little structure for encoding what type of file you think you're operating on, so you hopefully don't make mistakes. This one is saying this is the 17th operation specific to files in proc. There's some other sort of metadata here of here's the size of the structure, here's read, write, etc. We are not going to be able to evaluate this all the way to an integer. It is an integer, but we're not going to be able to figure that out just by going and reading kernel code. I mean, we can, but I do not have time to go through 10 levels of kernel files and do a whole bunch of math. So I'm going to cheat. And I'm going to write myself a little C program, which just prints out the value. So it includes this header file and prints out the value of this number. And I'm going to copy that number to my Python code and put a comment saying how I got it. One important thing is the actual values here are potentially architecture specific. I think most common platforms will use the same ones. I believe this value is correct for ARM64 and x86-64. So almost everyone here, this is the value you want. But it might be different on certain machines. And again, this is something you'd have to handle better in production code. There are some other ways you can handle this problem. If you check out the GitHub for this talk, I have an approach using a third-party module called CFFI. I don't have enough time to go through CFFI in detail, which is good because it turns out there's a whole bunch of stuff you can do with just the standard library. CFFI lets you write tiny pieces of C code on your own and access them in Python. So you can just ask CFFI to do this evaluation for you. There's a longer description up on the GitHub. I won't go into more detail. So one last thing before we are ready to put this all together is we needed to make that buffer to store our string. And there's a bunch of ways you can get buffers in Python. There's like the byte array built in. One of the things about byte array is it doesn't give you a way to get the address of the buffer. I don't know why this is. I know some of you are maybe going to think, well, what about the ID function? There's this undocumented thing where ID gets you the address. That's going to give you the address of the Python byte array object itself, not the buffer it contains. And so I don't think there's a way to do it with byte array, so I'm going to use the ctypes module. Ctypes is a really useful module. It does a whole bunch of stuff, again, which I don't have time to cover here, kind of solving the same problems as CFFI, but in a different way. But all I'm going to do here is ask ctypes to create a buffer for us, and then use ctypes' function to get an address of it. And then I can slice this buffer and get some bytes out of it, so I can see it creates a 1024 byte buffer and it's all filled with zeros, hopefully. And so that's all the info that we need to go put this together. So here is a little bit of code. I'm going to put this in a function. I'm going to create an object of that data class. I'm going to set those two flags I talked about earlier. I'm going to start at address 0. I'm going to set this VMA name field saying, please fill in this buffer. And then I'm going to just go into a loop and say, try calling this ioctl on whatever procmaps file I have open. It throws a standard OS error, file not found error, when it gets to the end of the list, which I found by just trying it and seeing what error it throws. And we take the bytes that were returned in the buffer. We decode that into a string in the standard way that you decode OS stuff into strings in Python. Throw the interset, and then go back to a loop and start querying at the next address. And so I wrap this in a function, and here is the code, and this full code, again, is on GitHub. And this is what it looks like. This is actually mildly buggy. I need to go fix that. I didn't realize that before putting up this slide. I fixed the bug, but I didn't fix the output. I think the version on GitHub is fixed. And that is our second example. I have a couple of things I want to talk about before we wind up, and we'll hopefully have a tiny bit of time for questions. Just to share, how do you find out what's new in the Linux kernel? This is what I use to pick the examples for the talk. LWN, originally Linux Weekly News, they now cover more than Linux. They now publish more than weekly. They are fantastic. They subscribe to a bunch of mailing lists, watch discourse forums, go to conferences, and they do some real journalism. And everything they publish is free. I am a happy subscriber because they paywall content for 1 week. So everything that's new, anything under active discussion, but everything on this talk is more than a week old. It's in a published kernel, so it's all free online. And apart from discussions, they publish summaries of the merge windows. This is the part of the Linux kernel release cycle where they're open to new features. And so that is what the article we were looking at earlier. And then kernel newbies, kernelnewbies.org is another great resource. They've got really detailed change logs of just about everything that goes in the kernel. If there's an article from LWN or a blog post, they'll link to that. Otherwise, we'll just link to the commit. Links to both of these again on the GitHub for this talk. And a couple more things to check out further. As I mentioned, there is a whole lot of the ctypes module that we didn't need to use. It's most useful for talking to other C libraries where you're doing normal function calls. There are times when it's also useful for talking to the kernel, like brand new system calls, etc., although those are relatively rare. I mentioned CFFI earlier. There is a full example of this procmap query in CFFI, also in the GitHub. There's Cython, lets you write a Python-like language that compiles to C. I happen to see on the schedule there's a talk later this afternoon called Cython in Practice that looks pretty interesting. If you need more control than that, you can always write Python extension modules in C, and then you're writing real C code. This is how CPython itself is implemented. This is how the fcontrol module, the OS module itself is implemented. You will get to the full level of power. If you need that much control and you don't want to write C, one really cool option is you can use Py03, which lets you write Python extension modules in Rust. And then there's stuff in the Rust universe like bindgen for interoperating with C. Rust is much closer to C than Python, so doing the work in Rust is a little easier, but there is a learning curve to Rust, but once you get past it, Rust is much better at making sure that you're writing pretty relatively correct code and not making issues with memory allocation like you would in C. Again, take a look at the GitHub if you missed any code or you want to see the CFI example. And with that, thank you all for coming. I think I have 30 seconds for questions, or feel free to find me up here around the conference. Right, so question is, how would you know if you got this struct bytepacking recipe wrong? And the answer is mostly, with the approach I have here, you wouldn't. You would be entirely on your own to make sure you're correct about it. One of the nice things, I didn't get to cover this in much detail, about this particular struct is everything is exact type 64 or 30-bit integers, and it's also packed. So you'll notice that the 32-bit integers are in pairs, so there's no gaps, et cetera. If this is not true, there's some rules in C for handling, gaps, for handling alignment, for, lots of things. The CFFI example that's on my GitHub actually compiles C code. So it's a little bit harder to get started with because you need not only a third-party module, but also a C compiler on the system you're using to build. And also, there's some setup steps. It's not just run some Python code. But that will actually compile C code, figure out what the offsets are, and that will handle this for you. So if I was going to do this in production, I would do this with CFFI, but there's a lot more to get started with, and this works fine for simple examples. Any other questions? I don't know if we have more time for questions than Mike. Okay, yes. Feel free to kick me off stage if we need this.
I just had a question about the very first use case. Maybe I missed something about that. You were talking about, opening a file. Did it create a new file? Did it not?
Yes.
Maybe I'm just lazy, or maybe I'm just in Windows more often, but why wouldn't you just call os.path.is a file to see if it's a file first?
That is a good question. That is, in fact, approximately what systemd was doing before they added this code to the kernel. The problem is if you're working in a directory that other people, other processes have access to, it might be the case that you get the response from os.path that exists before you try to create it. And so the idea is the kernel knew exactly what it did, and you want a reliable answer.
Cool. Thanks.
Thank you.